the last talk of this session is from Georgie Das from MidOpt, who will give us deeper insights about filters. So, Georgie, stage is yours.
Okay. All right, I'm assuming everybody can hear me. My name is Georgie Das. I'm with Midwest Optical Systems. We're located right outside Chicago. We manufacture optical filters and optical components. Today, I want to share with you about how you can create and have consistent and high-quality imaging, which is made easy by using optical filters. My colleague from Edmunds alluded to optical filters, but I want to impress more about how important they are when you're designing and deploying a machine vision optical filter. What's a filter? A filter is simply an optical component that goes on at the end of your lens or sometimes before your lens in front of your camera sensor. It's going to control what wavelengths are entering your vision system, which wavelengths are being blocked. When you're looking at an optical filter, you're going to see something like this. This is a transmission curve. It lets you know how a particular or specific filter is going to perform. It's going to let you know what wavelengths are being passed. That we refer to that as the transmission. So when a filter has high transmission, that wavelength, there's a lot of that wavelength being passed. When we talk about the pass band, we refer to the width or the wavelength region. Out of band blocking is how much or what part of the wavelengths are being blocked. The left side of the curve we call the shorter wavelengths. It's the UV visible. The right side of the wavelength spectrum we call the longer wavelengths, like infrared, shortwave infrared, and so it goes on. And so why do you want to use a optical filter? To create consistent and high quality images. Oftentimes, we're designing an application in a lab setting. The application, you get it working perfectly. It's working exactly right. But then you move it to the customer site or the factory floor, which often looks like the second image, right? There's all this lighting, all these windows. There's people walking around. Things that you could not account for when you were designing it in your lab because you didn't know what the customer site was going to look like. And so as I continue, we want to show you how filters are going to help. And at Midwest Optical Systems, we consider filters a necessity, not just an accessory. Oftentimes when you're designing an application, you think about your lighting and your lens and your camera, and then you think about a filter as an accessory. If you have problems, maybe you'll consider using one. But again, my goal here today is to show you that filters are absolutely a necessity when designing an application. So filters help with a lot of things, but today we're going to briefly talk about how filters help with creating contrast in your application, how they can help with resolution, how they increase repeatability, how certain filters can reduce glare or color correction, and simply how filters can help you protect your lens or expensive components. The first thing we'll briefly talk about is how filters help to increase contrast. In machine vision, of course, contrast is the name of the game. You're trying to achieve contrast. You're trying to create some kind of difference between your background and foreground, or trying to read an image from something else. Contrast is what you're trying to create. Filters, in this example, bandpass filters, do an excellent job of creating that contrast, okay? In my original color image of these red and blue caps, I have excellent contrast. I can easily tell the red and the blue apart. But what if I was using a monochrome camera or monochrome system? Suddenly, the contrast goes away. Here, I'm using a couple of bandpass filters to create that contrast. I'm using the red bandpass filter up top to pass the red wavelengths and block the blue ones. It helps to create that contrast, because when you pass a wavelength in a monochrome system, it highlights it, and when you block the wavelength, it darkens it. I'm doing the same thing in the image below with the blue bandpass filter. I'm passing blue wavelengths, and I'm blocking red ones. So the blue ones become highlighted, the red ones become darkened. Typically, when you're using a bandpass filter, you're matching the filter to your light source. So red light red bandpass filter, blue light, blue bandpass filter. Typically, that's what you do. But what if you're using a UV light source? Well, you might immediately think, okay, well, I need a UV bandpass filter. But the thing to remember here, when you're using a UV light source to cause something to fluoresce, you want to pass the emission wavelength. So what's being emitted. And so you're matching the bandpass to what the emission wavelength, not the UV excitation wavelength. So filters help to create contrast. Filters can help to create increased resolution, especially, again, if you're dealing with application that's in a monochrome, or it could be a single wavelength area that you're looking at. There's a type of distortion that occurs in lenses called chromatic aberration. It happens when lenses are trying to focus many different wavelengths, because many different wavelengths have different convergence points in the lens. If you don't care, if you're not looking for all those different wavelengths, you can use a filter to, again, limit the number of incoming wavelengths and possibly help your lens to become more efficient in almost creating a better resolution, higher, sharper image. One thing I mentioned is how filters will help you improve repeatability. All right, we talked about that where you're designing your application in a lab kind of setting. You get it working, and then you move it to a customer site. Well, now you're getting all sorts of read errors. The application is not working like you expected it to work because you've introduced lights and windows and people walking around and reflections, things that you could not account for in the lab. But had you used a filter from the very beginning, you would be controlling what light is entering your system and what light is being blocked. Okay, so ambient light, interfering light could potentially not be a problem if you used a filter from the very beginning. So we talked briefly about bandpass filters. Let's look at a few more. We'll look at some images and how they can help. Short pass filters, just like the name says, it helps to pass shorter wavelengths and block longer ones. These are also called IR cut filters. They're often included on color cameras, but sometimes in machine vision they're not, or you might want to upgrade your type of filter. In this application, we had a customer who put lots of cameras around their football stadium. When they're looking at their image, they're seeing a weird pink and red hue to the image. That's because the camera sensor was picking up a lot of infrared from the stadium lights and from sunlight. Our eyes aren't picking it up, but the camera was. And so adding a short pass filter helped to pass those shorter visible wavelengths and block those interfering longer wavelengths to help produce that natural color rendition. Like short pass filters, long pass filters pass a certain wavelength region. Long pass filters help to pass longer wavelengths and block shorter wavelengths. This is very essential if you're working with near infrared, especially if you're working in near infrared using a standard CMOS sensor. This type of filter will block those shorter wavelengths and visible wavelengths that you're not interested in looking at, help to increase the efficiency of that standard sensor where there's a little bit of responsiveness in the IR. In this example, I'm just using some clear water bottles. I'm using an IR light source. I'm using a long pass filter, which lets me see how that water is absorbing that infrared. In this image, I'm doing something very similarly. The infrared or the long pass sensor is helping me see how the stitching on the watch band is being reflected. So again, creating that contrast. Polarizers are a very useful type of filter when we're dealing with glare, when you're expecting something shiny. Polarizers are very helpful in reducing that glare, helping to better see what you're inspecting. A couple of things that you have to keep in mind when you're deciding what kind of polarizer to use. Number one, what is the light source that you're using? Is it a visible light source? Is it an infrared light source? What is causing that glare? After you know what's causing the glare, you can decide between a linear polarizer or a wire grid polarizer if it's infrared. The next thing that you have to keep in mind when using a polarizer is you have to polarize both your lens and your light source. Okay, you have to do both to help reduce that glare in an optimal way. In this example, we have a customer who's looking at some beer bottle labels. It's highly reflective. It's difficult to see the alignment and the text on the label. In the first image, I have no filter. It's very shiny, very reflective. Then I add a polarizing filter to my lens, and you can see there's not much difference between the first two images. But then I polarize both my filter and my lights, for both my lens and my light source. You can see there's a drastic reduction in glare there, much easier to see. Finally, I use a red bandpass filter. I use a red bandpass filter to limit some ambient light and to help reduce the reflections on that label. So polarizers, great way to combat and help reduce glare in your applications. Multi-bandpass filters are filters with more than one bandpass, or more than one passband, I should say. There's dual bandpass, triple bandpass, very useful in an assortment of applications, especially if you're looking at ITS, license plate recognition kind of applications. In these type of use cases, there's usually two cameras, one for the day, one for the night, or you have a single camera with the filter that switches in and out depending on daylight illumination and then infrared illumination. But with using a multi-bandpass filter, you can have multiple passbands, one channel for visible light and then one channel for infrared. So that you can use one camera, one lens, one filter. This will do twice the work. There's also a line of SWIR filters. SWIR is a trending kind of wavelength right now. We're hearing a lot about it, and it's very useful for lots of different types of applications, most commonly inspecting fruit, silicon wafers, looking at fill levels. You might see a lot of applications around autonomous vehicles that are using SWIR wavelengths. You want to use filters because they help to enhance your sensor, because they're blocking visible light, blocking potentially interfering wavelengths from your SWIR wavelengths. So again, another reason why you'd want to use optical filters. Again, my colleague from Edmunds touched base on this. Sometimes you might not need to increase contrast, but you might need a way to protect your lens or create some kind of protection for your camera components. And filters are a great way to do that. Offered in both glass and acrylic, and using optional coatings, you can enhance the protection that these filters offer. This is an example of a protective window that has an oleophobic coating on it. This prevents grease or oil from sticking to the front of that protective window. This particular window has a hydrophobic coating. This almost works like Rain-X on the windshield of your car, helps to prevent condensation and liquid from building. This is another example of that hydrophobic coating. If you look at that first image, you can see the fog kind of building and sticking on that window. On this one, it doesn't, which has the coating. So these types of coatings, again, when you're using them with protective windows, you have a very robust solution for all types of application: food and drug, outdoor, aerial, all sorts of applications. Another kind of coating that you might be familiar with is AR coatings. Again, these are applied so that there's not much loss of light. When light passes through glass, there's some reflections that happen. You can lose 8 to 10% of light depending on the substrate that you're using. These AR coatings help to reduce that amount of glare so you don't lose that light. That first filter that you see there has no coating, so there's lots of reflection. The second one has a mag fluoride single layer coating. The reflection is reduced. In that final image, I have a broadband AR coating, a multi-layer coating that's really helping to reduce that loss of light and loss and reflection. So filters help with all sorts of different things. We covered a few of these today: contrast, resolution, repeatability, reducing glare, color correction, protection. They can help with lots of different applications. So again, my hope and my goal is that when you're designing an application, when you're thinking about lenses, lighting, camera, also think about filters. One of the best ways to decide which filter that you need to use is to use a filter kit. These types of kits have multiple filters in them so that you can test and see which filter is going to help best. If you'd like to win a free filter kit, please stop by my booth. It's in Hall 10, booth number 52. Drop in your business card, and we'll be glad to give you one. We'll ship it to you in a few weeks. Again, my name is Georgie with Midwest Optical Systems. Thank you so much for your attention and for your time, and thanks for allowing me to speak here today. Thank you.
Okay, thank you very much. Okay, because we have to stay in time, there's room for one question. Yep, please.
It's a really simple one. What's the upper limit of your broadband anti-reflective coatings? Are you going into the sphere yet, or?
Not at this time. No, it's I believe right around 900 or so, 900 nanometers.
Thank you.
Okay, Georgie, thank you very much for this nice visualized presentation. Thank you.